Hello guys, in this video we are going to continue with derivatives. The objectives of this video, the objectives are to review the first derivative test and the second derivative test, although we are only going to use the first one, okay? We will put examples in which we apply this first derivative test and requirements, as usual. For sure, we are going to calculate derivatives. We need some calculus manipulation, algebraic manipulation, and concepts like derivatives and functions. Also important, it's the critical point definition. Remember that a critical point is a point for which the derivative of the function is equal to 0, or the derivative at this point does not exist. Okay? So in order to calculate critical points, what you need to do is to calculate the derivative of the function that you are given, equal the derivative to 0, and solve for x, or the variable that appears. This is tricky. This is difficult sometimes, so be careful. Calculating critical points, sometimes it's a piece of cake, nothing to do, but sometimes it's a little bit complicated. Okay? Okay, let's suppose that we have the critical points. What is the first test derivative about? Okay, the idea is to study the sign of the derivative. You need to know, or you need to remember that if the derivative of a function at a given point is positive, then at this point the function is increasing. If the derivative at a given point is negative, then the function is decreasing. So, how do I know that a critical point is a maximum or a minimum or a saddle point? We say this is an inflection point or a saddle point if it is not a maximum or a minimum. Okay? So, with this test, if the derivative changes from positive to negative, then the function has a local maximum. If the derivative changes from negative to positive, then it has a local minimum. And if the derivative does not change sign at this point, it's what we call an inflection point or a saddle point, okay? That test makes sense if you just breathe and read it carefully. With all the information we have, it's nothing to prove. Remember, derivative. Positive means the function is increasing. Negative derivative, the function is decreasing. So, if the function is increasing and then it's decreasing, this function is a maximum. If the function is decreasing and then it's increasing, this middle point is a minimum. Okay, it's just logical. In the last case, the function is increasing, seems it's going to be decreasing in the next step up, but oh no, it's going up again. And then what differentiates this point to any other point of the function? Okay, be careful. We say that it's a saddle point if the first derivative is equal to 0, and then this rule applies, and then the function does not change, or the derivative doesn't change sign. Okay? It's not difficult. These three properties has to be practiced in order to understand completely what are we doing. Okay? So, let's see examples. The first example we saw on the other video was x squared minus 2x plus 1, a polynomial of degree 2. The derivative is piece of cake. I hope this part is easy for you. The derivative of x squared minus 2x plus 1 is 2x minus 2 because of the rules of the derivatives. Nothing really difficult. Okay, if we equal this derivative to 0 and solve for x, what we obtain is x equals 1. This is the critical point, okay? And we are cheating in this example. I just provided the plot of the function, so all of you can see that this point is a global or absolute minimum. It's a local minimum, but in this case it's also the absolute minimum. Because the function is still is not going to change, it's increasing here, and in this part it's always decreasing, so it's going to be the global minimum. Okay, but how do we know? How can we prove that this is a local minimum? Okay, or a global minimum. In this case, local minimum is the answer. Okay. Let's see. Let's plot the derivative. Here you have the derivative. The derivative is just a straight line, a slope 2. So it's going up all the time. At the point 1, the derivative is passing from negative values to positive values. Okay, perfect. So in this case, what this means is that the function, the original function, not the derivative, the original function is decreasing until 1 and increasing after 1. Okay, remember the relation between the sign of the derivative and the increasing, decreasing properties of the function. Okay, so when the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. Okay, so piece of cake. But again, we are cheating because you see the plot of the graph of the derivative. And looking at this graph, it's very easy to say that, okay, before 1 the derivative was negative, after 1 the derivative was positive. This is not the technique we are going to use. We need to do it in a mathematical way, not plotting these things. Okay, and how do we do that? Okay, it's not difficult. And the key points, I will try to explain the key points of this method okay, following the slides, but just keep focus on what I'm saying also, okay? So, and I'm following, by the way, I'm following the same structure of the slides, okay? So you have a critical point, one critical point. One critical point divides the real line in two parts. And you see here the two parts. From -1 till 1 and from 1 till plus infinity. So one critical point, we have two intervals, okay? The derivative does not change sign except in one, maybe, okay? So once you have the critical points, and this point divides the straight line in two intervals, we need to check the sign of the derivative at each of these intervals, okay? It's not going to change the sign in any other place because of how we are calculating things. So one critical point divides the straight line in two intervals. How do I know the sign of the derivative at each of these intervals? The ones you see here, from -infinity till 1 or 1 plus infinity, piece of cake. Take any point you want at each interval. Which value is perfect? No value is perfect. Sometimes it's easier to calculate or not. What have I done? In the interval -infinity 1, I took the value 0. It's the one I choose. You can choose a different value between -1 and 1. Between -infinity and 1. Okay? Any value in between, it's perfect. I just took 0, as I told you. The derivative at 0, it's -2. Oh, but I don't remember the derivative. Here you have 2x minus 2. If I change x by 0, I got -2. So I know that in the interval -infinity 1, the derivative is negative. And that means that the function is decreasing. Perfect. The other interval. What happened to the other interval? I need to take any value in between 1 and plus infinity. I decided to take 2 as the value. You can choose any other value. It doesn't matter. And replace this value in the derivative. I don't remember the derivative. Okay, let me show you here. This is the derivative. And I'm changing the value of x by 2. This is 2 times 2 is 4, minus 2 is 2. Okay, that is the value you got here. Okay. The number, it doesn't matter. In fact, I'm just trying to guess which is the sign. And in this case, the sign is positive. And what does this mean then? This means that the derivative at 1 plus infinity interval is positive. And also, this means that the function is increasing. So, putting everything together, between -infinity and 1, the derivative is negative, the function is decreasing. From 1 till infinity, the derivative is positive, the function is increasing. Okay, applying the test of the first derivative, the derivative passes from negative to positive. That means that it's a local minimum. It's also a global minimum because the function is decreasing all the time, increasing all the time, and then it doesn't change signs in any other place, so it's going to be the absolute minimum. Okay? So it's not complicated. It's the first time it takes time, but if you practice these ideas, I promise you it's not going to be any problem. Okay, a little bit more difficult exercise, but I'm going to do it faster this way. This example is just to scare you a little bit. You see a polynomial degree 5, this takes time. Okay, I tell you. It's not so easy. Even I just prepared the exercise to obtain critical points that are integer numbers. If they are not, this could be almost impossible to solve. But okay, so you have a polynomial of degree 5. The critical points were calculated in a previous video. It's negative 1, 1, 2, and 3. Okay, perfect. So we have 1, 2, 3, 4 numbers, 4 critical points. These 4 critical points divide the real line in 5 intervals, as you see here in the slide. From minus infinity till 1, from minus 1 till 1, 1, 2, 2, 3, and 3 plus infinity. And we need to study the sign of the derivative at each one of these intervals. So we are going to check the sign of the derivative 5 times. I know it's boring, I know, but let's do it. Here you have the summary of all the calculations. In the interval minus infinity minus 1, the point I chose to replace it was negative 2. So the derivative of negative 2, the derivative, by the way, it's a polynomial degree 4. It's not written here. You can. I'm just trying to continue from the previous video. Just take a look to the previous video or calculate the derivative. It's very easy in this case. The derivative is at negative 2 is 60, positive. Perfect. So the derivative at this interval is positive. Means that the function is increasing, by the way. For the interval minus 1, 1, I chose 0 as the point that I'm going to take. In fact, I don't have many other integers in this interval. The derivative at 0 is negative 6, negative. The derivative is negative at this interval. So this means that the function is decreasing in this interval, minus 1, 1. For the interval 1, 2, I choose 1.5. The derivative is positive again. So the function is positive, is increasing at this interval. For the interval 2, 3, 2.5, in this case is negative. So the function is decreasing. Finally, for the interval 3 plus infinity, I choose 4. At 4, the derivative is positive, then the function is increasing. So, what can we say about the critical points? Look, at negative 1, the function passes from increasing function to decreasing. Increasing, decreasing. Okay, local maximum. At the point 2, look, the function passes from at the point 1, the 1 is where the interval changes. At this interval, the function passes from being decreasing function to increasing function. Decreasing function, increasing function, local minimum. The same happened at the point 2. At the point 2, it changes from increasing to decreasing, local maximum again. And finally, at the point 3, the function changes from decreasing to increasing, local minimum. Here you have the summary. At minus 1, local maximum. At 1, local minimum. At 2, local maximum. And 3, local minimum. Okay, do you want to see this in a picture? You can just use Python, for example, to plot the function and see where are the maximum and minimums. But mathematically, this is perfect. Okay, so we just discovered which are the critical points. The second derivative test only uses the second derivative in order to know if a point is a local maximum, local minimum. In this case, let me review that. If you have critical points and the second derivative at this point is positive, then we have a local minimum. If the second derivative is negative, then we have a local maximum. And if the second derivative is equal to 0, then we don't know. Or we need to apply another technique. Okay? So, what have we seen? We have reviewed the first derivative test, and we use it in an example. The second derivative test is just mentioned. You can use it. And by the way, if you want a little bit of homework, you can just apply the second derivative test to the previous example. So you double check that the maximums and minimums are what they are supposed to be. Okay? So guys, I hope you find this information helpful, and thank you for your attention.